Anyway, so I'm going to talk about the transport layers. I work in the transport layers. So Yuliang, my student, is really the expert. I'm just presenting his work. So we have seen that applications have increasingly requirements on high throughput, low latency network. For example, for cloud storage, they of course want high throughput. They send lots of data, but they also increasingly want low latency. As the storage techniques improves from hardware disk to non-volatile memory, they start to want more and much lower and lower latency. Similarly, for distributed deep learning, a lot of us use, they have faster and faster CPU computing resources, moving from CPU to TPU. That means it's important for the network to keep up so that it doesn't become the bottleneck. And also it means that for a lot of applications, if we can enable more data transfers across the network, that means we can do less job at the compute node that will actually make them more efficient. So network is also important for these kind of applications. And finally, for the new trend of resource disaggregation, network also play a critical role. On the other hand, if we look at the trend of high physical network improvement, we actually have been quite successful. For the past around 10 years, we have moved from like a total of 640 G to about 12.8 terabytes. So each port can now reach 400 gigabit Ethernet. So we are very successful in the physical layer as well. But in order for the high applications to get the high throughput and low latency, to fully use the high-speed physical network, what we're missing is actually a high-speed transport layer that can match the two. So what are the challenges of optimizing transport layer? We have many challenges. Inside the network, we have diverse applications and coexistence of these many applications. So that means we actually may face a lot of hard balances of network utilization, latency, throughput, and stability. For end-host part, it's the same. We have different workloads. That means operators have to do lots of job to customize different transport layers and parameter settings to get the best performance of the for this specific workload. So that means end-host won't be settled with a single transport layer protocol. And on top of both challenges, we have increasingly larger network. That means we will have more flows, more packets that we have to understand their dynamics. So what are the opportunities? Opportunities comes from the physical network layer. We have better devices, better switches and NICs that's getting more efficient and more programmable. We also have more processing and storage as hosts for us to collect more detailed information. So the key opportunity we see here is that we are now entering an era we can collect lots of detailed information. So that means we can get detailed understanding of application workloads, detailed understanding of the impact on performance of different transport protocols, different parameter settings. And finally, we can enable more fine-grained control of the queuing behaviors of the network. So in this talk, I'm going to just give you two examples of how detailed information could help. The first example is about Deterred, which is about a diagnostic tool for transport layer that by collecting detailed yet lightweight packet level information at host that can help us understand how transport layer behaves. The second part of the talk is going to be about transport optimization. We will show that how detailed information about queuing behaviors can help us optimize transport protocols better. So I will start with the first part, Deterred, Deterministic TCP replay. So how many of you have been need to debug your TCP performance of applications in your life? Right? There's a lot of us. And it's the same for operators, except that they're facing much larger networks. They have to continuously debug their networks, TCP transport layer, to be able to optimize performance for their new hardware and new applications. And one thing I want to stress here is that tail latency matters a lot. Like it's very easy to debug a problem when your average throughput is bad, but if your tail latency is bad, you have to really capture that corner case and understand what's happening for that corner case, and that's really challenging. But But in general, why diagnosing TCP is hard, why we find it painful, because what we learn in textbook is that TCP is just a simple state machine with 3 states in the sender layer. The receiver just send X. But if you look at the Linux TCP implementation, we have so many modules. And these modules actually have very complex interactions with each other. So for example, the receiver window manager may send some messages that trigger the loss recovery module to ignore some duplicate, and in the end, it wouldn't even enter the fast recovery stage. That would affect your TCP performance. Some other weird cases could be like the receiver end could ignore some packets because it's feared of attacks, and that would cause the send window manager to not send any traffic. So the TCP connection actually pause for a while. And it's actually even more complex in that if we look at TCP, Linux TCP, it has 63 parameters. A lot of the parameters are actually unknown to a normal application developer. Some experts may know all of the parameters, but even to set the right parameter is a challenging job for experts. They have to rely on try and errors to see, like, if I tune the parameter a bit, how much would they affect the performance? Only until several tries they can identify the best setting. That's quite complex. And TCP is also under continuous and error-prone development. We just looked into 2 months in 2018. In Linux TCP, there were like 18 bugs reported and need to fix. So how do we diagnose TCP today? I'm sure you have used this tool, TCP dump. It's very effective. It provides a lot of detailed packet information for us, except that this tool is actually 20 years old. And over the past 20 years, the bandwidth has increased from 10 megabps to 100 Gbps. The network size has increased from tens of hosts to hundreds of thousands of hosts. So use the TCP dump tool that used to be very effective now becomes very hard to use just because it has too much overhead. We cannot afford to run them in production network. And this is similar for many other debugging tools we have been facing. There is a fundamental tension between getting more and more details about the protocol versus we want low overhead so that we can run it all the time. So if we look at all the tools exist today, there's some tools like TCP dump, TCP probe that can provide lots of details but with high overhead. There have also been some of the tools that aims to be lightweight, like eBPF, TCP counters, but they may miss some information which are critical for us to debug the performance problems. So existing tools cannot achieve both because it makes this seemingly right assumption is that the thing you record is the thing you can use to diagnose. But this is not true. For our friends in distributed system community, they have actually been using a quite effective tool called Deterministic record and replay. So there they can collect some lightweight information in the runtime, but just replay the whole protocol again, they can collect more data for diagnosis at the debugging time. So that's exactly what Deterred is trying to achieve. So in the runtime, we want to collect some lightweight record information. So because it's lightweight, we can run it all the time and capture the information for all the connections in the entire network. But when we've identified problems, we're going to enter the replay phase where we can collect information for the specific connection experiencing problems, and we're going to deterministically replay this information. And during the replay, we can do all the kind of typical debugging we wanted to do. For example, we can capture packets, capture counters to understand it more. We can also trace executions of the TCP protocol to see which process function it enters. We can also iteratively diagnose the process to understand more and more about the problem. Okay, so how do we apply the same idea for TCP? One strawman solution would be let's just record all the socket calls, right? So if we can record all the socket calls and replay them on exactly the same server environment, the same TCP, Linux TCP code, then maybe we can reproduce the same stream of packets, the same stream of behaviors, so that we can diagnose the problem. But unfortunately, if we just simply replay the socket calls, we won't get deterministic replay. Why? That's because actually there are many non-deterministic behaviors in the entire network. We have many switches in the middle that could take different actions. Through these switches, there could be many other connections that interact with this connection that are causing problem. Inside the kernel, there could be even more non-determinism. So the key challenge Deterred trying to address is that first, network-wide, how do we capture all the non-determinism that happens at the interactions between switches and hosts? And second, how do we capture all the non-determinism in the kernel? So I'm going to first talk about the first challenge, the interactions between the switches and TCP, which we call the butterfly effect. The interactions actually mostly happens because there's a closed loop interaction between TCP and the switches that amplify the small noise into dramatically different network behaviors. So here's a concrete example. Say we just have two TCP connections. There's the blue connection and the orange connection. So the orange one arrives at a near full queue first. So the blue one gets dropped in the runtime and causing performance problems. But when we do the replay, even when we replay in exactly the same environment, we may still face small timing differences because we cannot control exactly how the packet enters the network. So say we have just a few microsecond differences of how the packets enter the network, it will be likely that the blue packet now arrives first. So the orange packet gets dropped. And what happens next is that it's going to cause different TCP behaviors. So in the first case, it's the blue connection which back off. But in the second case, it's the orange connection that back off. And if we imagine that there are a different queue in the network that the orange connection goes through, that means some other connection, some green connection that used to be affected because of the orange connection sends lots of traffic. Now in the new case, because it's a blue, it's back off. The green packet traffic is actually fine. So that you can see it will just keep propagating. A lot of connections are going to be quite different. It's not deterministic replay. So how do we address this problem? Well, we have to break down this closed loop interaction, the butterfly effect, by just capturing the switch and TCP interactions. So if we can cut the closed loop interaction and record replay also the connections in between, then we would address the problem. But that would mean that do we record all the packets into TCP? That's very expensive. So what we do is we find out that the majority of packets are actually fine because TCP are performing in a deterministic way. The major difference is actually what the switch actions, which we call packet stream mutation. It really just means packet drops, some ECN bits, some reordering, any of the action that switch takes. So, and it turns out that these kind of packet stream mutation are quite lightweight, because if we look at drop rate, it's typically low in the entire network over a long time. ECN is just 1 bit per packet, and reordering is also rare. And so if we can capture the host switch interactions, then we can also replay each TCP connection independently, because different TCP connections actually interact with each other through these switch actions. And more than that, we don't even need the switches for the replay because we have already recorded all their actions. So this means that we don't even need to replay all the connections in the large network at once. We can actually take one connection at a time and replay it. So the second challenge is there are lots of, yeah, go ahead.
The last slide, so what are you actually capturing?
So we're capturing packet loss, ECN, and any of the switch actions, but loss and ECN are the major actions.
So for example, a particular byte sequence number, if that packet was lost or not.
Yes.
And that is captured via whether it was retransmitted or not.
Yeah, we captured by comparing the source, sender and receiver packet streams.
And the timing? The timestamps, because without timestamps you won't be able to do it.
So I'm going to talk about time span the last, but the intuition there is similar to distributed system. there they don't really care about the timestamp that a specific request gets sent. They really care about the ordering of events, right? So here it's the same. We really care about how these events happen comparing to a lot of the end host behaviors. But as long as we get the ordering right, a lot of the problem can be solved. We don't really rely on exact timestamp. Where there are some corner cases that rely on exact timestamps, but so we also provide timestamps. But I want to make sure you understand that deterministic replay doesn't require accurate timestamps.
So you record only at the two ends, nothing in the switch itself?
Yeah, we don't record anything at the switch. We only need access to the end host at the two end hosts. That's why this is targeted as a
timing, but it needs to be some synchronization between exactly two endpoints, right?
So I'm curious because when you say that, yes, exactly. So there has to be some notion of because so when you say that deterministic replay does not require timestamp,
yes.
I'm confused because consider the example that you gave, right?
Yeah.
I have no way to correlate whether the green packet and the orange packet drops are related or not. Because maybe two flows are dropping packets separately or they're dropping packets.
Sorry, so the question is TCP gonna react to this drop event, right? So as long as this drop event is in the order with the socket call events, the decision events, then it's fine. And also the other packets, like when I make this decision, the other packets are affected. So as long as the packet stream, the socket calls and these decisions are in order, then it should be fine. It doesn't really matter when the packet exactly dropped in the switch because we want to just cut the interaction. It's really when the drop is affecting the decision, right?
So you care about the orange flow independently of the blue and the green?
Yes. Because the rate, the other flows affected is through packet drop. And we already capture packet drop, and we make sure that it's in order with the other decisions. Make sense? Yeah.
What about some dynamic things that could happen in the kernel stack, like for example GRO that have timeout or
yes.
interpolation, NAPI, those things.
Yes, so that's actually the second challenge. There are actually some non-determinism happening within the kernel. Typically, there are like some handler functions, OS calls. There are also some thread scheduling and also some kernel variables TCP actually reads. So we have to capture these kind of kernel events as well and replace them in order with these packeting events. But fortunately, these kind of events are much simpler for TCP comparing to a normal distributed system application. So we can actually do many customizations on how to capture these events so that we actually need only a few bits to capture them efficiently. So for example, for thread scheduling, TCP actually just have one lock for connection for all these threads. So as long as we capture that lock behaviors, we will be fine. Okay, so as I mentioned, timestamps are not critical for deterministic replay, but sometimes people are used to debug problem by looking at the TCP dump traces, and for there they would expect the packet to have some timestamp information associated with individual packet. So for that, we actually allow you to recall the sample timestamps and infer the rest of the timestamps with bounded arrow. So a natural approach to do such sampling is that we can do gap-based sampling. Basically, TCP typically send packets in batches. So if we can capture the timestamp for a batch of packet, we can actually infer for the rest. But unfortunately, it's not as that accurate because you can see for some TCP behavior, for all the packets within the batch, it could have different rate. So instead, we do kind of rate-based sampling that just computes the rate changes of individual packets, and whenever it changes, we sample it differently. And we can actually get to very accurate timestamps. So at the tail, 95% tail is like 3 microsecond differences, and at the full 9 tail is actually 5 microsecond differences. It's actually good enough for us to even simulate queuing behaviors inside the network. Okay, so we actually implement Deterred tool in Linux that just need 139 lines of code to add to Linux to instrument it. And it actually achieves quite lightweight recording. So including all the timestamps, kernel behaviors, everything, we take only like 2 to 3% of storage overhead comparing to compressed packet header only traces. And the CPU overhead is less than 1.5% in collecting the data in the runtime. So now let me show you how we use the tool in reality. So we actually take like 20 servers in EC2 and we run Spark there. We try a TerraSort application with 200 GB TerraSorts. And this application actually has 6.2K connections. So we basically run Deterred for all the connections in the runtime, capture all the lightweight information. And then we take all the flows that experience 99.9 percentile tail latency. Because we have information for all of them, we can actually do a survey for this application, which flow has what kind of problems. So for these tail latency flows, we can see that a lot of the small flows have retransmission timeout and fast recovery. Some other larger flows have delayed ACK. And we actually have a lot of detailed information about these flows, so we can actually zoom in to understand individual flows accurately. So we take one delayed ACK flow, we can use Deterred to replay it, to redraw the complete sequence graph. So we can see clearly from the sequence graph that there is a pattern between like burst of traffic and then 40 millisecond delay and then the ACK. So through replaying, we can actually trace the behaviors and understand that it's because the receiver TCP stack has entering a buffer shrinking stage, and because of the receiver CPU is actually overloaded. So that just show you how we can leverage Deterred to do like large-scale accurate detection. Here's another example. We actually, yeah, go.
Was there any other disturbing traffic, or it was just purely Spark? I mean, UDP and DNS queries and things like that.
So we don't have access to production network. So what we do is we run our own application, trying to debug our own application. If you have a mix of traffic, we can also diagnose that. The UDP and other kind of traffic are actually much simpler because they don't have the complex TCP reactions. You can simply use Deterred to just capture them as well.
It shouldn't really.
Sorry?
It shouldn't really matter whether or not.
Yeah, if you end up having complex interactions, we can capture them. TCP is actually a harder example. Yeah. Yeah.
Can you also, this Deterred tool can also answer questions like whether there was congestion in the network or
yeah, so I'm going to actually show that. So far I've been showing, maybe we can wait until this example. So I don't need to flip slides. So there's another TCP stack example before I talk about network. So in this example, we have a toy example, 2 senders and 1 receiver, some long flow, some short flow. And we run it different times, but one time you could see a problem of one short flow experienced 49 millisecond delay. Right, so this is kind of the weird case that it's very hard for you to diagnose with your intuition, because here in our testbed, the RTO is 16 milliseconds. From TCP counter, you expect like maybe there are 2 RTO, but it's still much less than 49 milliseconds. So because Deterred can show you detailed packet level behaviors, so we can actually use the information to draw the TCP sequence behaviors, and we can see that actually the 2 RTO are consecutive. So because it's consecutive, it's actually entered this exponential backoff space. So we have actually 16 milliseconds and 32 milliseconds. But why do we have consecutive RTT retransmission timeouts? It's because the receiver doesn't send the ACK, right? Then it raises the question of why the receiver doesn't send the ACK. So we actually can replay Deterred again, use Deterred to replay again. And this time we track the function call graph inside TCP. And there we can see that the receiver actually entered the delayed ACK function. That actually causes a problem. So we can see that you're using TCP counters, you may be able to get to the first stage, knowing that there are 2 retransmission timeouts. But you really need a lot of detailed diagnosis and debugging to be able to understand the remaining of the debugging process. Okay, so there are also many other reasons that could cause retransmission timeout. So if you just get a counter called the retransmission timeout, you can't really know how to fix your bugs. So what about the queuing problems at the switches? For that, because we actually reproduce all the packet traces with relatively accurate timestamps, we can actually run a simulator with this large network and inject all the packets into the network so that we can replay the queuing behaviors inside the network. We also showed one example in the paper that have actually a temporary black hole issue caused by switch buffer sharing. And through simulation, we can also debug this kind of problem. There are some limitations that we may not be able to get the accurate switch queuing models in simulation, then we couldn't do it. But today, some vendors already provide such accurate simulators.
And does this work even if you're going through several switches? Because
yeah, so this is a real...
interactions are complex.
Yeah, so we can actually run a large network. That's what I mean by simulation. Because if it's just one switch, we can just run it in testbed as well.
And this thing does not require the path information?
Oh yeah, that's another question. We have to make sure the replay is the same as the path information, as a routing, path, network configuration. Everything has to be the same to be replayable.
How do we get that information? Do we capture that in Deterred, the switch?
That's like out of Deterred's picture. It's really about your operating network. Can you capture routing behaviors? And you can do it, yeah. Great, so hopefully in Deterred I showed you how detailed information could help you diagnose your TCP performance problems. And Deterred really provides you a light way to record and replay so that you can get such detailed information. By the way, the tool is open source. You're really welcome to use it. And let us know if we can improve it. So now I'm going to talk about how detailed information of the queues inside the network. Yeah.
One question about Deterred. So here you're sort of diagnosing in hindsight, right, what went on, but it seems like a lot of the information you could use also for alerts, right, because you have visibility into the kernel, right? So
yes.
Some of these examples, right, the RTO is over something, it could be one of three reasons, you can look at what the end host actually did. So did you look at these online mechanisms for saying
so the key challenges the key challenge is really diagnosing is really hard problem that requires human involvement. But for known bugs, you can of course use Deterred to like automatically replay if it sees a long tail latency, can replay and check. But for the problems that if we don't know ahead of time, it's actually really hard. It really needs humans still. Okay, so I'm going to show you another example of using detailed information. So if we have detailed information of queuing behaviors inside the network, how it can help us improve the transport performance. And we were focusing on, so this is in collaboration with Alibaba Networks, and we were focusing on RDMA. So RDMA's key idea is that TCP stack is really slow. Let's get rid of them and bypass it so that we can use a NIC to do most of the packet handling. So that way we can significantly reduce the CPU overhead and we can get ultra low latency, less than 5 microseconds. Because of this ultra low latency, it causes lots of problems in congestion control. One of the fundamental problems for RDMA is actually the congestion control. So in networks, we worry about packet losses, we worry about long latency. But if you can do congestion control right, these kind of problems can be eliminated. These are higher level problems on top of congestion control. Okay, so I'm going to just show you a few abstract examples on Alibaba's experience of running RDMA in their production network. I won't be able to show their concrete data stuff, but I'm just abstract away a few examples so that hopefully you can see a few experience of how operators think about congestion control in their production network. So the first example is PFC storm, priority flow control storm. So PFC is a strategy for us to push back flows when congestion happens. But from operators' point of view, they really view this as last resort. Like they want to avoid it as much as possible. The reason is that like when PFC is wrong, it will cause lots of problems. So for example, incast is actually a typical congestion control problem. It gets more severe for RDMA because RDMA can push more data much faster inside the network. And so once these operators see an incast together with a vendor bug, so the incast trigger PFC, and the vendor bug causes the PFC to keep sending. So that causes the PFC storm. So basically, when you see a PFC storm, it pushes back all the upstream senders, not only in the incast traffic, but also other senders. And it pushes back multiple hops ahead. So it has a pretty large impact in the entire network. And because of that, they learned the lesson and know PFC is bad. So they try to keep their link utilization low so that they can minimize the trigger of PFC without any new congestion control protocol. That's the best they can do. So from the example, we can see that it's actually very hard to balance the performance and link utilization. Right? Operators typically go for low link utilization so that they can get better performance, but it's really expensive. So here's a second example. So they have very long latency for their machine learning application. This is larger than 100 microsecond average latency. This is typically not a problem for TCP, but for RDMA, it's like very bad. Because for RDMA, the tail latency is just less than 15 microseconds. So to debug this kind of ultra low latency, because this low latency behaviors is more sensitive for RDMA than for TCP. So what they actually find out is that it's what we all know, like some storage system that's occupying the queue so that the low latency traffic could not go through. So again, operators don't have any expertise in improving their congestion control. So what they do is they put ML in a separate cluster so that the two traffic are isolated. But what that means again is that the ML has this cluster has low utilizations. And it actually faces a hard trade-off between low latency and high throughput. So what is the state-of-art congestion control protocol for RDMA? It's DCQCN. There are many other variations. Timely is another one, but for this data center, they use DCQCN. So there are typically two key ideas in DCQCN. The first idea is rate-based control. It's try to have very fine-grained rate control instead of using windows so that they can tune the rates more effectively. But unfortunately, associated with rate-based control is that you also have many parameters to tune. Specifically, you have these timers for you to decide when to increase the rate and when to decrease the rate. But it's very hard to get the timers right. So if you get the two timers too close to each other, that means you can actually be more sensitive to the congestion behaviors, but it will become less stable. But if you make it larger, then it goes like more stable but less sensitive. So there's actually a very hard balance between performance and stability. The second idea of DCQCN is to use ECN bits to send feedbacks so that we can react to the queue buildup before the packet loss. But it's also, again, very hard to set the ECN threshold, right? If you set it too large, it's in favor of large flows. If you set shorter, it's in favor of small flows. It's, again, very hard to balance the delay and the throughput traffic. So the key question is, can we achieve a good congestion control protocol that can achieve low latency, high throughput, and also high bandwidth utilization and stability?
What do you call stability?
Stability means that when you can have a burst of traffic, you want to react to it. But if you overreact to it, then your network basically go up and down, right? So that's what happened for DCQCN if you don't, you're not careful enough in setting up the threshold. Okay, so this is kind of magic. Can we achieve all these goals at the same time? But fortunately, we have some kind of leverage, which is there's new switch capabilities. Today in Broadcom and Barefoot switches, we actually have this new capability called in-network telemetry that allow us to put switch queuing behaviors into the packets and carry it to the receiver and then send it back to the sender. So by leveraging more accurate information, maybe we can do better.
Who uses in-network?
Vendors. So vendors provide these capabilities. Alibaba actually start to experiment with this, but the other networks I'm not sure. Okay, so that's basically HPCC's key idea. We can use INT to provide precise control. And because we get the precise information, we can get both high throughput and stability because we can quickly use the capacity of the network, the free capacity, and avoid congestion. We can also get high bandwidth and low latency because we can get close, very high utilization and get close to zero queue. So, yeah.
Sorry. Can you please go back one slide here?
Yeah.
The in-network telemetry is layer 4 or the buffer status?
So in network telemetry, because these switches are kind of programmable, it allows you to put any kind of switch information inside the packets so that you can carry over. So for our design, we put queuing information like queue length information and what the timestamps of them.
The buffer status.
Yeah, the queue length information and also the timestamps the packet arrives when the queue is high, and also the bytes you send when the packet arrives. This kind of detailed information.
And this is and the packet is sent, and who reads it?
Sorry? Oh yes, so the end host can read it.
Switching between buffer, which is and the TCP state is layer 4, and the buffer status is layer 2, 3.
So the packet sends through the network. The switch puts this queue information inside the packet header, and then the packet reaches the receiver. That's where we pass the packet information, retrieve the information, and put in the ACK and send it. So it's the same as ECN, right? ECN is switch marks 1 bit. Here you can mark more information and carry it, but the whole process is the same as ECN. Okay, so if we compare with DCQCN, what we try to do is first we want to improve rate-based control by combining with standing window constraint. We will talk of detail later. We will try to improve ECN-based backoff to more like precise information, INT-based backoff. And we're also trying to improve its heuristic adjustment based on different thresholds, based on now accurate adjustment, because now we have the exact queuing information. So this slide is probably a bit more complex. That shows how exactly we're computing the rate based on the queuing information. So first, this part we probably can ignore for the talk because it's just about additive increase. It's not about congestion. So during congestion, it's mainly this formula that's taking effect. It's basically for flow rate J. We try to adjust the flow rate based on the target input rate and the normalized input rate. So target, we certainly want it as high as possible, but we then check all the links in the network and trying to see like what the current input rate is. If it's lower than the target, then we try to increase it, but if it's higher than the target, then we try to decrease the rate. And then how do we get the input rate? We get it from the INT information. Basically, we get the queue length information in the switch, and we get the output rate times some baseline RDT. So these together will capture the amount of in-flight packets in the network, and we use that to compute the rate we see for this packet. Does it make sense? Yeah.
How often can you read the queue length?
So that's a good question. So for INT, it's really every packet going to capture this information and carry it.
Oh, I see. So this information is piggybacked on the packet.
On the packet, yeah.
Perfectly, it's like a sort of glorified version of ECN, where you just having 1 bit.
Yes, exactly. So now because of the new capabilities, we can get more information.
Get more bits out of it.
Yeah, and we actually, there's something new that we only realized only until recently, is that we comparing to XCP kind of design, right, that also uses this 1 bit, and we carefully compare the format of this formula, and we find out that because here we use accurate queue length, there they use inferred queue length from the ECN bit, right? And because of that, we actually choose to use output rate. Like they were mostly mirroring input rate. The reason is that if you think of the input rate, inside input rate to a queue, it actually already captures some of the queue length information. So because we now have more accurate such information, we're able to use the output rate to avoid the redundancy. And because we avoid the redundancy, it actually makes the network more stable. Like there, they have to add another extra parameters to handle the stability of the protocol, but we don't need it because we get accurate information. So there are many kind of implicit things we only realize as we understand more and more about the protocol, what it means to get precise information.
What do you mean by output rate exactly?
Output, it's about the queue, like in this switch per port, like you see when the packet gets out. Input rate is when the packet gets into the queue.
Right.
Yeah.
And this queue length is because most of the switches I assume are shared buffers. This queue length is telling you per port queue or the entire.
So the queue length is what are the packets that are blocking this current packet from getting delivered.
So it's,
right.
It's a per port queue.
Well, if you have shared buffer part that's also blocking the packet, you should also count it, right?
But it's per output port or input port?
Oh, per output port.
And that so the UI is computed at the sender, right? Because only
at the sender
knows the
yes.
baseline RTT, for example.
Yes,
right?
yes.
And how many packets does this translate to? So when you send this, sorry, how many bits does this translate to? So when you send the packet through this entire...
I forgot. We can check the paper and I'll let you know. But it's minimized, I think. I probably have a percentage number later in the slide. Okay, so this is a basic idea, but I'm going to go to a few observations we have. The first is like rate-based control. So people typically like rate-based control. Like DCQCN use rate-based control for a reason, because it's trying to, comparing to a window-based control, it's actually trying to have more fine-grained control, right? So window, you send a batch packet, you wait for an update, and then you send. But for rate, you are computing the rate. That means you can actually sparse out all the packets before you get an update. So that's actually the intuition of DCQCN, of why it chooses rate-based control. But unfortunately, it happens. This theory only holds when you have low congestion, right? Why? Because during congestion, your RTT gonna be inflated. So that means the time you get the update gonna take much longer. So when it takes much longer, when you have rate-based control, you actually send more packets than a window-based control system. So window-based control system actually has some benefit in that it bound the amount of in-flight packets. So during more severe congestion, you can see that rate-based control may have longer feedback delay and may cause you to send more extra packets. So that's why, although we also use rate-based control, we try to also bound the in-flight packets. And to bound it is actually really simple. We just compute the rate and baseline RTT. But we make sure that we don't send too much traffic into the network. And this figure basically shows that we're able to reduce, during a simple in-cast behavior, we're able to reduce the queuing behavior very low comparing to a DCQCN setting. Okay, so there's another subtlety here, which is that we get the information per packet, right? Every ACK we get such information, so we keep updating the rate. But it turns out that if you keep updating the rate, you may be overreacting to the system, right? So for example, if the first packet shows me that I'm congested, I'm gonna reduce the rate. But the next time I see the follow-up packet also see almost the same queuing behavior, I'm gonna reduce the rate again. So you can see it could cause pretty bad behavior. I keep reducing my rate because now I have more precise information. It actually makes it bad. But we also don't want to go back to per RTT because that means we just update the rate slow. We also lose the benefit of INT. So instead, we want to have a way to combine per ACK and per RTT behaviors. So what we do is that we set this rate, the original baseline rate, to be per RTT. So that if I have multiple packets arriving, I always compute it based on the baseline RTT. So avoid me to always reduce my window, reduce my rate. But if the two packets carry the same information, I reduce the rate the same way. But at the same time, we keep this UI always updated, right? Because the in-flight packet is always updated. So if the multiple packets, if the one packet carry different information, even within the same RDT, we're able to capture it, and we're able to update the rate. So that in that way, through this combination, we can get fast reaction without overreaction. There are also some theoretical property we were trying to prove for HPCC, I will skip. We actually implemented HPCC with FPGA as a host sender because we need some changes at the NIC. So there we implement the congestion control module and the flow scheduling module on top of normal forwarding behaviors. Okay, so here I'm just going to show you some results. The first one is a testbed result with web search traffic. Working at 50% workload, we can see that HPCC in the medium is comparable to DCQCN, but in the tail it actually reduced the flow completion time a lot. And if you look at the queue length, this is really near 0 queue across all time, while DCQCN have some long queuing behaviors. We also run a much larger time scale, simulation with Facebook Hadoop traffic plus some incast. And we can see that HPCC gets also the lowest performance. And we can see that if we add our window budget to DCQCN kind of protocol, we can also improve DCQCN to some level as well. But really, all the design in HPCC is important in that it brings the FCT time pretty low. And if we see the PFC pausing behaviors, which HPCC, we actually don't have any pausing behaviors, while the others may have some. Okay, so in conclusion, hopefully through the two work, I showed you how important it is to get detailed information for both diagnosing the transport protocol, but also to optimize it. Yeah, that's it. Question?
Seeing that.
Thank you.
Actually, Frank Kelly, Professor Kelly seems to be involved.
Yeah, he was helping a lot on the theoretical part.
Is there anywhere I can read about? I imagine something.
Yeah, I mean, we will publish in SIGCOMM, we will have appendix that have all the theory.
So it will be in
stuff.
this year's SIGCOMM.
Yeah.
I'm trying to understand, Minlan, are there obvious scenarios where DCQCN would be better than HPCC?
We haven't seen any. But do you have any intuitions on why it would be better? Then we probably can try it.
No, I'm curious if you've thought about it.
Because I don't see why it's, we get more information than ECN, right? So.
Well, by the same argument, you may be reacting much more quickly than DCQCN, where reaction will not be necessary.
But we avoid the reaction already, the overreaction already.
Yes, I'm curious if you've thought about it.
There's nothing coming to my mind. Yeah.
Okay,
Great.
the speaker
Thank you.
again.